All right, let's take a look at the next set here. We are on page, I don't know, maybe 4 on this one. Sorry, page 3 took forever. Okay, so these are kind of interesting ones to graph, particularly the first two. You can't enter r squared into the graphing calculator. If you look at the kind of input, notice it's just r. So what we want to do when we are actually inputting these is, sorry, wrong thing, is you want to square root both sides first and rewrite this. Remember, when you square root both sides, or any even root, write it as a plus or minus. Now the square root of that constant multiplier is easy to do. And then we have the square root of cosine of 2 theta. So I'm just going to graph that and see kind of what happens when we graph that. So there's really 2 different equations here that I'm entering in. The first one is positive 2 times the square root of the cosine of 2 theta. And then the next one would be negative 2 times the square root of the cosine of 2 theta. Now, I already entered in the first one. You can see it's like that infinity symbol. Watch what happens with the next one. It just traces over it. These are actually the same graph. Both the principal square root and the negative square root actually just trace right on top of each other. What happens here is what that negative does is just pushes it over to the opposite side here, right? And the opposite side just like reflecting it over the y-axis, if you will. And since it was already symmetrical around the y-axis, it just traced over itself. So this is an infinity symbol. And if you look at the length of each of these petals, the length is 2. So this ends up looking like that. This has a name. I'm just going to scroll through. This is called a lemniscate. A does need to be positive in order for it to be symmetrical to the x-axis. And if it's positive, A, with a cosine, it'll look like this. Now, A is the square root of this leading coefficient, and that will tell you the length of each of these 2 petals of your infinity symbol. This is super interesting. If A is negative, it flips this to being around the y-axis, which is really weird since this is cosine. Really, really weird. And then also in a rather bizarre fashion, the sine ones, if A is positive, if A squared is positive, this is in like quadrants 1 and 3 versus if A is negative, it's in quadrants 2 and 4. Weird. And they don't show up a lot. I'll be honest with you, you're only going to do lemniscates a couple of times. So not a ton, but that's kind of how they work. So this one would be, remember these were like along the quadrants 1 and 3. And so the length here, A, is actually 2, which is the square root of 4. And so this would be like an infinity symbol like that. And if you graphed it, you would see it. All right, this last one's super fun. It might be different than you think. Let me just make a table of values really quickly. If I pick 0, then I would have the point 0, 0. If theta is like pi over 6, then r is pi over 6. Now remember, r is like 3. So like 3 over 6, like a half. So in the direction of pi over 6, I'm going to go like half a unit. If I did like pi over 3, that's close to 1. So in the direction of pi over 3, it's about 1. If I do pi over 2, this is like close to y 1.5. So like here. If I did something like, I don't know, 2 pi over 3. Remember, pi is close to 3. Notice the input and the output are the same. This is like in the direction of 2 pi over 3. This is like 6 over 3. This is kind of like 2. If I did pi, then this is pi. In the direction of pi, it'll be 3.14. And we can keep going. What it ends up looking like is something like this, which is really weird. And I'm just going to graph it so you can verify I'm not doing this incorrectly. So let me clear all of this out. And then clear out this one. And so this one's just going to be pi. Sorry, theta. Oh, I guess I didn't clear out my second one. Fail. I did something wrong. I don't know what. Okay. This actually has a name, And by the way, if we continued making our domain bigger, I just went around 2 pi, it just continues to spiral around and around and around. This is called Archimedes' spiral. It's a pretty cool little graph. Archimedes is a Greek mathematician. So this is Archimedes' spiral. Archimedes one time was doing a geometry problem. He was doing it in the ground, in the sand or the dirt or whatever. And his city-state was actually under attack from enemy soldiers. And he was so engrossed in what was happening with the geometry problem he was working on, he had no idea that they were even under attack. And actually a soldier came up and killed him with him being totally unaware, which is kind of a bummer. But also, I guess he died happy. He was doing math. I'll let you put whatever you want about what you notice about these graphs. I have from here just kind of a summary of these values. This video is probably way better than anything I could come up with. So I encourage you, if you're having some trouble, you're just not feeling like you're being very successful with these patterns, this video could help. Here's a nice little summary. We didn't really talk about what happens when A is negative, but for our circles, cosine's still along the x-axis, but just on the negative side. If A is 0, sine's still on the y-axis, but on the negative side. For our cardioids, remember, that's when A and B are the same. If we have a negative leading coefficient here, or sorry, not a leading coefficient, a negative value in between A and B, so subtracting, it just pops this over into the other side. If you make a table of values, you'll see that. Same thing with sine. The bulk of this would be over on the negative side. Your limasomes with dimples or limasomes with dimples, if there's a subtraction between them, again, it just flips it over to the negative side of the x-axis. Cosine is still around the x, sine is still around the y, but with that minus, it just flips it. The inner loop, you're going to see the same thing. If we have the minus, it's just flipping it over. And if you make a table of values with your quadrangles, you will see that. Rose curves are the hardest ones. There's some little notes in here that you could look at. I hope I did a good job of stating some things that are mostly true. I really kind of have to really look at each rose curve pretty individually. All right. These next ones, our job is to graph these without a graphing calculator. So put your graphing calculator away. Some kids freak out. They do not like these graphs I gave, but they're kind of nice for graphing polars because they have those little circles, okay, around to help you plot these. So our goal would be to figure out what the patterns are and to identify them. This is a rose curve. I could identify this because of the fact that I have the multiplier of theta, and I'm not adding or subtracting anything. It is not a cardioid. It is not a limosome. It is a rose curve. And so I have an odd number, so there will be 3 petals of length 2. I'm going to create the boundary points by setting this equal to 0. So I'm looking for where sine would zero out if I divide by 2. And so the angles where sine will zero out will be at 0, pi, and then I could keep going around the circle 3 full times. I'm probably, I guess I'll do all of them just in case you need them. Usually students, once they've done a couple of these, they kind of get the pattern. But so theta is going to 0 at 0. When theta is 0, that will be a boundary point, or boundary. I'll just put it as a boundary, like little segment here. At pi over 3. It's nice because these ones have the angles labeled. At 2 pi over 3. At pi, when I reduce, you can kind of see this 4 pi over 3. 5 pi over 3, and 2 pi. Now notice that these are 6 regions, but I only have 3 petals. So what that tells me is I'm only going to be using every other region. That will happen when you have, oops, it's backwards, when you have the odd multiplier for your angle. I'm just going to pick one that's kind of in the middle of a region that's easy for me, like pi over 2, and evaluate it. 3 times pi over 2 would be 3 pi over 2. The sine of 3 pi over 2 is -1 times 2 is -2. In the pi over 2 angle, I'm going in the -2 direction. So 1 petal is here. If I then skip every other region, I can draw in my picture. Oops, that's not 2, that's 3. And there's my graph. Number 6 is another rose. Notice that this is an even number, so there are 4 petals of length 4. I'm going to set this expression equal to 0. I'm looking for where cosine would zero out, which would be at pi over 2, 3 pi over 2. And I'm going to have to go around the circle twice since this is multiplied by 2. So that would then be 5 pi over 2 and 7 pi over 2. I'll divide. So theta, we would have boundaries where theta is equal to pi over 4. This is one place where the pedal would dip back to a 0, okay? Those boundaries are where the pedal would go back to the origin, so like the starting and stopping points of pedals. This would be 3 pi over 4. That's really enough for me to kind of see the pattern that these are all going to be the pi over 4s. And then because there are 4 regions and 4 pedals, each region will have a pedal of length 4. You don't have to draw them in the order I draw them in. That was not the right width. Try to make them like kind of fill the space. I didn't do a great job with it. Probably this pedal's probably like the best one I made. All right, number 7. This one, since we only have one trig function, nothing's being added. I don't have a multiplier. This is a circle. The diameter is 4, and this is along the y-axis and in the positive direction for pi over 2. 1, 2, 3, 4. So I'm just going to draw a circle to the best of my ability. That's great circle. That's a great circle. I taught geometry for 25 years. That's what's so sad. This one is a cardioid because A and B are the same. This is a cardioid. So I'm looking for that heart shape. I should see this go right back down to the origin. I'm going to go ahead and use my quadrangles to help me. When you get more familiar with them, you won't need to do this as often. But anytime you're just like not confident, this is a good method. So if I plug in a 0, cosine of 0 is 1. That's where it zeroes out because we get a -1 for cosine of pi. So I'll plot my points. 1, 2, 3, 4. 2 in the pi over 2 direction. This is where we have the dip of the heart for the cardioid, and I'll do my best to draw my curve. It should look like a heart. The cardioids always have that dip right at the origin. This is not a cardioid. A and B are different. Now, since A is smaller than B, this tells me we can dip into a negative direction. This tells me that this is a limosone with an inner loop. Okay, if this output could be negative loop, then you will have that inner loop on this. Okay, now, because this is symmetrical around, this is cosine, it'll be symmetrical around the x-axis, but because of this minus, we're going to see it's going to be on the left side of the x-axis. You can see that pretty easily when you plot some points. Again, using the quadrangles is usually going to be enough information for you to feel like you know where to go, as long as you're recognizing the shape. All right, 0, cosine of 0 is 1, 2 minus 3 is -1. Now, to plot that, I'm going -1 in the 0 direction. This is, by the way, my inner loop right here. That's the end of my loop. Pi over 2, cosine zeroes out, so 2 minus 0 is 2. At pi, cosine of pi is -1, so this would end up being a 5. 3 pi over 2, cosine zeroes out. So at pi, I'll go in the direction of 5, or in the direction of pi, I'll move 5. 1, 2, 3, 4, 5. And 3 pi over 2 is 2. Oh, this one's also 2. All right. So now, these inner loop ones do go to the origin. They're always going to go to the origin as kind of the start of that inner loop. You've got to pass through 0 before you can get to negatives. This sounds a lot like IVT here. These are continuous relations here. Okay, this next one, A is smaller than B, which tells me I can get into negative values. So this is another limosone with a loop. And because this is a sine function, this is going to be symmetrical around the y-axis. And because it's a plus, it's going to be around the positive side of the y-axis. All right, if I plug in a 0 for sine, that will 0 out. At pi over 2, sine is 1. At pi, sine is 0. 3 pi over 2, it's negative 1. This is where I'm going to have my loop, right here when we dip into the negative values. But 0, we have 1. Pi over 2, we have 3. At pi, we have 1. And in the direction of 3 pi over 2, we need to go back to negative 1. There's the loop. I often draw that loop first and then try to kind of connect from there. Notice that these inner loop ones always are going to touch the origin. All right, we do not have anything added or subtracted. This is not a cardioid. This is not a limacone. This is a circle. This is along the x-axis, and we have the diameters too. Now you could still plot points with this, by the way. All right, I'll just show you in case you are ever wanting to do this. All of these you could plot points. It's not really needed in this problem if you recognize the form, but you could. Cosine of 0 is 1 times 2 is 2. This one zeroes out. This would be negative 2, and this would be 0. So in the direction of 2, or in the direction of 0, I'll go 2. Pi over 2, I get to 0. At pi, I'm going in the negative 2 direction. That's back to this point. And 3 pi over 2, I get to 0. You might see there's only these 2 points out of those. If I wanted more, like pi over 4, etc., I could definitely do that, but it's just going to go like that. Here's another circle. The diameter is 3 in the negative direction, and this is along the y-axis because it's sine. So I'm going to make sure and go in the negative direction. These will always touch the origin. Now, if it was r equals a constant, then it would be the center is the origin. Those are a little different. Like r equals 2 means the radius is 2 no matter which direction you go, and it would look like that. So that's the other type of circle that can show up. All right, on this one, A and B are the same. This is a cardioid. This is along the y-axis because it's sine. You don't have to plot points if you're starting to see some patterns. I won't grade you on plotting the points. This is just a strategy you can use if you find it helpful. So then if I get all of my values here, at 3 pi over 2 is where we're going to zero out because sine of 3 pi over 2 will be negative 1. Some things that sometimes students notice is that this diameter here of this cardioid is 2 plus 2, which is 4. Something like that. That wasn't so bad. You should look at that. That's like maybe the best cardioid you're going to see from me all year. Okay, this one. A is greater than B. Because A is greater than B, we will never be able to get a negative output. The smallest cosine could ever be is negative 1. This one's never going to touch the origin. We also cannot reach 0 for our radius. We also cannot ever get to an inner loop because we can't have negative values. This will be a limacone with dimple. So it'll look a lot like a circle, but it'll have like one little place where it's not super symmetrical. And again, knowing the forms will help you anticipate, and getting a few points is a good idea. All right, so this would be 5, 3. Here, remember cosine of pi is negative 1, so those are going to subtract off. So 0, 5, pi over 2, 3, pi 1. There's where your dimple is going to occur. That's where it's like you lose your symmetry a little bit. And so it'll look something like this. There's that funny little dimple there. All right, on this one, A is smaller than B. And since A is smaller than B, this is going to have that inner loop. This will be a limacone with the inner loop. We should anticipate that this will be along the cosine, or since this is cosine, this will be along the x-axis for its symmetry. And since there's a minus here, we will see that this will primarily be on the left side of our graph. But if I plug in some numbers, I'll get negative 1, 1. Now right here, cosine of pi is negative 1 times negative 2 is positive 2 plus 1 is 3. By the way, where you have the negative, this is where your loop is. This is the loop, the like longest point of the loop of the petal that's formed by the loop. And 1. So 0 will go in the negative 1 direction. Pi over 2, 1. Pi will go in the 3 pi over 2, 1. I usually draw the loop first and then just kind of continue on. I try to make this kind of circular here on that part. All right, on this one. Oh, something else I should mention about these lemniscapes, they will always have a 2 theta here. And so it's not quite the same as a rose, right? A rose, we would think that would have 4 petals, but look for that r squared. So A is 3, which is the square root of 9. Cosine, if cosine's positive, will be, these are like our infinity symbols. They're called lemniscates. And so we're going to have this infinity symbol here. 1, 2, 3. You could plot points to see that. Okay, if you wanted to plot some points, you could. Right here, sine, again, A is positive. So A is 3, which is the square root of 9. And this is also infinity, but this infinity symbol is always going to be in 3rd and 4th quadrant here. And it's symmetrical. So it'll split right in the middle, so along that pi over 4. How wide is that? Probably, the petal's probably actually wider than I drew it. Sorry. But I'm just happy if you get the shape. All right, that is the end of the winter break assignment.